Circles in space, arranged to create beautiful ornaments. In order to better understand the three-dimensional sphere in four-dimensional space, I'm going to show you how to fill space with circles and thus create what mathematicians call a fibration. By the way, my name is Heinz Hopf, and I'm one of the main contributors to the development of topology during the first half of the 20th century. Look at this torus, filled with circles that appear to be linked. Let me explain this picture to you. Circles, spheres, and tori are among the simplest objects studied by topologists. A topologist tries to understand the connections between these objects. I worked in Berlin, Princeton, and Zurich, and one still comes across my name often in contemporary mathematics. Poincaré-Hopf theorem, Hopf invariant, Hopf algebra, Hopf fibration. Let me paint my portrait for you. I published the discovery of my fibration in 1931. But, as always, I have to say that I relied upon many predecessors, like Clifford, for instance, whom you see here, and who worked in England during the 19th century. Let's begin with some explanations on a blackboard. Well, a whiteboard this time. What do you see? A two-dimensional plane? Well, yes and no. This is indeed a two-dimensional plane, but it's a plane with two complex dimensions, or in other words, a space with four real dimensions. Give it a try. Each point in this plane is determined by two coordinates, but each of these two coordinates is a complex number, which, remember, is itself defined by two real numbers. Each of the axes is a complex line, so each point on a given axis has one coordinate which is a complex number. For instance, here you see the point 2 minus I on the first axis. The same is true for the other axis, the y-axis. Here we can see the point 1 minus 2i on this axis. Now, our whiteboard is magical, but not enough to be able to show us the two planes simultaneously. If we try to depict them in three-dimensional space, they will intersect along a line. But in four-dimensional space, they intersect only at the origin. After all, they are axes. Now what do you see? A circle? Yes and no. What you see, or rather, what you should imagine, is the set of points in four-dimensional space that are a distance 1 from the origin. In other words, this is nothing other than the three-sphere, S3. Well, of course, you need to have a little imagination. Let's try to see at least how this sphere intersects the first axis. The three-sphere intersects the first axis in the set of points on this axis which are at a distance 1 from the origin. You see, the three-sphere intersects the first axis in a circle. The same is true for the second axis, which intersects the three-sphere in a circle as well, the blue circle. Now, What is true for the horizontal line and the vertical line is equally true for all lines going through the origin. Here you can see the line with equation z2 equals -2 times z1. But we could do the same with any line, z2 equals a times z1, for any complex number a. In this manner, the three-sphere in four-dimensional space is filled with circles. One for each complex line through the origin in our plane of two complex dimensions. Careful, though. In the picture, you get the impression that the red circles intersect each other. But this is not the case in the four-dimensional reality. Lines meet only at the origin, so their intersections with the unit sphere don't intersect at all, in fact. I discovered some very interesting things about this decomposition of the sphere into circles, and ever since it is known as the Hopf fibration. Why fibration? Well, you could think of the fibers of fabric. We are going to look at all that using stereographic projection. Imagine that we project the three-sphere from the North Pole onto the tangent space at the South Pole, which is our three-dimensional space. Here is the projection of one of the circles, which, as we have seen, is the intersection of one complex line and the three-sphere. But there are many such circles, one for each complex line going through the origin. For each complex number a, we can consider the line z2 equals a times z1 and its associated circle. Let's vary this number a, or what will amount to the same thing. Let's rotate this line in order to see how the circle changes. Notice that sometimes the circle appears to be a straight line, but this is simply because it passes through the North Pole of our three-sphere. Let's look at two of these circles simultaneously. In the lower left-hand corner, you see two moving complex points, one red, the other green. You can see the circles associated to the red and green points. Note that these two circles are linked together like two links of a chain. It is impossible to separate them without breaking them. Just for the fun of it, let's consider three circles. See how the three linked circles dance together? Now let's take many more complex lines, chosen randomly, and let's look at them all at once. The circles fill space, and no two of them intersect. This is an example of a fibration. Let's try to understand this better by returning to the board for a moment. Look, we have a Hopf circle for each line. Each one of these lines has an equation of the form z2 equals a times z1, where a is a complex number, the slope of the line, and is indicated by the red point moving on the green line. Actually, the vertical axis does not have such an equation, but in this case, we may say that a is infinite. Don't forget that a is a complex number. The green line is also a complex line, so it's a real plane, of course. Summing up, the complex lines that we are interested in are completely determined by a point on the green line and an additional point at infinity. But we already saw that if we add a point at infinity to the complex line, we get the usual two-sphere. Once more, this is stereographic projection. So, the complex lines that interest us are parametrized by points on the yellow sphere, the two-dimensional sphere S2. So we have a circle for each point on the two-sphere. But a circle is a one-dimensional sphere, isn't it? All these circles fill up the three-sphere. Each point on the three-sphere belongs to a single circle and therefore defines a point on the two-sphere. In this way, we get a projection from the three-sphere to the two-sphere. Complicated, isn't it? Mathematicians say that above any point of the base, S2, there is a fiber, which is a circle, S1, and that the total space of this fibration is the sphere, S3. I am very proud of my fibration, all the more so because it has become a fundamental object in topology.